Welcome back. So the electric field. So I did a video with regards to kind of the gravitational force field, and I'll put up a link up above there. I think that it's worthwhile for you to watch it. It was kind of an introduction to vector fields in general, and it's much easier to be able to understand it because of the fact that typically when you study physics on the foundational side, you begin with kind of going back into from kinematics to dynamics, and in dynamics, when you study forces, you talk about Newton's law of gravity, and that particular law of gravity allows you to expand and try to understand vector fields, in particular the gravitational field that is present. So I encourage you to kind of watch that in before you get kick-started on this one. So the electric field. So now we're going to try to shift that concept that we learned from the gravitational field to the electric field, where basically we're trying to figure out what are all of the forces that are present at any point with regards to charges. So here is kind of the definition that you have for the force caused by kind of the electric field. So what you have in here is the following. So this is nothing else but simply just the force, and that particular force, you may recall from Coulomb's law, is or can be captured by simply this particular equation, where K is your constant. Okay, you have two particular charges, and then they are separated by a certain distance, and we're assuming that they're kind of point charges, or at least they're concentrated, okay, within a very small radius, and they're far apart enough that this particular law will apply. Now, this, of course, is hand in hand with that gravitational law. That's why I encourage you to try to go over it. And I am assuming that you're familiar with this Coulomb's law right here. So this is the actual force that we have between any two charges. So you might ask, well, what is the need for this electric field, okay, and the introduction to it, if we can just take Coulomb's law and find out any force that we like on a particular charge? And you're correct, we can certainly do that. Now, we can expand it a little bit further, and the electric field, as you keep studying electricity, does come pretty handy as you keep moving forward. So it's good to be able to understand what this field is all about. So if you can see here, so I have kind of taken these two. Now we're going to assume we're going to drop the absolute values. Please recall that the absolute values were nothing else, okay? So they just serve the purpose to remind us that charges can be both positive and negative. Unlike, for example, the law of gravity, where everything was positive and it was always an attractive force between two masses. Here, okay, we have, of course, charges that can be like and unlike, and like charges are going to be repelling each other, and unlike charges are going to be attracting each other. So that, you should still remember from Coulomb's law and charges in general. So here, what we have is we're going to be relating the actual force present. Okay, so the E just stands for electric. Okay, so this is the electric force that we have. The Q, of course, is just going to be nothing else but a charge. And you can take any charge and you want to find out what is the force on this particular charge from an electric field. Now, please note, okay, so, the symbol for the electric field, I don't really like utilizing capital E per se, because it relates it back to energy. And I do remind you that, this, you might see it in textbooks, not necessarily written out as just a capital E. You might also, see it written out like this, where you kind of utilize an epsilon. But again, an epsilon is also used for other things in the electric world. So which symbol you use won't really matter as much. The idea is, can we understand this concept? So this is going to be our electric field. So now the question is, of course, what is it, right? Okay, so we have Coulomb's law. We have this kind of definition where we're multiplying a charge times the electric field. And if we do this multiplication, we're going to get what the force is on this particular charge at any point. That's the same thing, okay, if we were applying Coulomb's law, okay, if there's only really two charges, or we can use superposition for multiple things. If you want to see a little bit more on Coulomb's law, I'll put up a link up above there for you, okay, so if you're interested or if you want to try to recall this. So let's dive in. So I'm going to, take a charge. So let's imagine that, we have a charge. I'm going to call this capital Q so it doesn't really sway into any of these Q1, Q2s or the smaller Q for the moment. But let's imagine that we have a charge. And let's imagine that it is positive. So when you're talking about the electric field, what we're really interested in is the following. If we had a test charge. Now, in kind of electricity and magnetism, our test charges are assumed to be just a positive test charge. That's purely by convention, all right? So it's nothing else but simply by convention. So if you have a test charge which is positive, and we don't necessarily need to know what the value of it is, but if we had this test charge, so let's imagine that it's, some small charge somewhere out here, and we wanted to find out anywhere around this particular charge, right? So anywhere we put here, what the actual force would be on it. Well, then we know that we can use Coulomb's law because we would have this test charge right here. So I'm going to put this little Q and put positive just so that you know that it's positive. And if you know that this charge was positive, the first thing that we should all know is that, hold on a second, well, I know that these two are going to be repelling each other. I'm going to assume that this one is static, so it's kind of stationary. So what would happen is you would get a force, okay, the electric force, which would be pushing it out, okay, away from that original charge. And of course, if you put this anywhere else, so somewhere within here, within here, etc., you always are going to see that, okay, so no matter what, you're going to have a force, electric force, which is going to be pushing it away. So now that's exactly what we want to be able to do. We want to try to take a test charge around some charge, which is either positive or negative, and see what happens. So I'm going to kind of remove this for the moment right there. And what we would now notice is that no matter where we would put this test charge, and if it was positive, again, we're assuming that it's positive, then what you would find is that you would have these kind of force fields. Okay, so you would have all of these kind of stemming out radially outwards. This is very much like your kind of, that you had your actual gravitational force field that you were doing. Now, of course, I can kind of keep going, and I think you get the gist that no matter where I would put that original charge, right here, that it would always be getting pushed away, as long as, of course, as it's positive, right? So no matter where, it's going to get pushed away radially out. That's what would happen. And now, so what we're doing is, we're creating, these are called electric field lines. So that is just telling us what would happen to any test charge that we would drop in here in the vicinity of this positive Q. Now, okay, if you had, so I'm going to kind of shift this away right here. Okay, I'm going to make it and shrink it a little bit in here. So now if you took the same, okay, so imagine that you had a charge as well, but you made this charge negative. Now, if you made it negative, then what would happen is, and you started to bring in this test charge anywhere near here, then no longer would it be radially outwards being pushed away. It's actually going to get sucked back in, assuming again that it's a positive test charge because the positive and the negative would attract. So what we would have is, instead of drawing these particular lines and then that they were going outwards to show that the actual force at any point is pushing it away, well, we would have lines, but the lines would be inwards, right? So they would be like this because of the fact that it is negative in here. So, you can continue this. I'm going to just draw a few here, and you can, of course, draw as many as you like right there. So this just tells us exactly what happens. So any positive test charge would just get sucked back in, so that there would be a force that is present. Now, if you want to know what exactly that force is, well, you certainly can utilize Coulomb's law, where you can name Q1 to be this charge and then Q2 to be this particular charge, and then you can see at the distance what is the actual electric force that is present. Now, if you remove this test charge, so if you now remove the test charge right here, so I'm going to just remove it in general, and you wanted to be able to find out, all right, well, what is the force per charge that is present at any point in time. Then what you can do is you can certainly take this Coulomb's law right here. So if I take this, now I'm going to kind of rewrite it for us right here. So we know that we would have that the actual force, I'm going to drop the direction in here, so we're going to only talk about the magnitude. So forget the actual directions, okay? If it's inwards or outwards, I think you understand, okay? So if you put a positive charge and it's a positive charge as well, then they're going to be repelling, okay, etc. So now what happens is we have this, we have K, we have our charge, which is Q1, multiplied by our charge Q2, divided by the actual radius squared. And if you now take this and say, all right, well, I want to know what is the force per the charge. And now let's, just for the sake of kind of this argument, I'm going to kind of pick on Q1, and Q1 would be our test charge anywhere that we would put, and then Q2 is just the actual charge itself. So I can divide both sides by Q1 in here, okay, and this would of course remove this, okay, right there, and what we would get is as an equation all of a sudden, so we would get what is the actual force present on the charge, so on the charge Q1, and it would be equal to just K times the charge that is present right there, and what is the radius in between them, or the distance in between, where this Q2 is nothing else but just this Q that is present, right? So that's what that Q is. And what it's telling you, at any point that you like, now this is, you know, a distance r away, you can find out what this value becomes. What is the force per charge? That force per charge we call the electric field force. So that is actual, it's a vector. We can find the magnitude, and this is the magnitude itself within here. So if you're going back, this is nothing else. Okay, this is what we define as the electric field. Now it is a vector overall, so it will have a direction, so depending on what you're setting. And as you can see there, so if you take this entirety, I'm going to put this back in here, so put this vector in here, so this is the Q, okay, so this is the Q1 that I have, I'll just change it to Q over here, so for any general one, and notice that you're going to come up with the equation, so this is going to be Q because you can multiply it and switch it over, and that will now tell you the exact force or the electric force that is present from the electric field itself. But the electric field is this right here. Now this is per one charge, so that Q that you have. Now of course you can have multiple charges, right? Multiple static charges all over the place, and you can use superposition in order to find what the overall electric field is at a particular point. So, for instance, when we're drawing these field lines like this, all the way through, right, and we're going all the way around, this is just with regards to one particular charge around. And it's very easy to understand that they're going to be radially outwards or radially inwards, just depends on what the charge would be. Okay, so now if you're going to be taking these and start to have multiple charges, right? So if you start putting one charge and another charge at a different point, well, then it's not going to be just necessarily radially out, because on a positive charge, what you will have is you're going to have multiple charges acting on it. So what I mean by this is the following. So what you can do is this. So let's imagine that we have, you know, two charges now. So let's kind of put one charge over here, and, you know, we'll put another charge over here. So what we will have, so if this is a positive charge, now it will now depend on the size of that charge. And let's say that this is a negative charge right here. This is what we would have. Let's imagine that the Q is identical. So this would actually be called a dipole. So di just means two, okay, that we would have in here. And as you can see here, so I'm going to now start sketching this out instead of just drawing really nice ones. If this was here alone, then the electric field would have been pointing outwards at any point, right? Because we have a positive test charge. If the negative one was alone, then the electric field, okay, would have been pointing inwards. It would be trying to suck it into that negative charge. But if you have both present in here, and now you put a positive charge anywhere, well, so for that positive charge, so for example, if it was somewhere over here, what you're going to find is that coming in from the positive side, you're going to have a force which is going to be pushing it radially outwards by this. But coming from this negative charge, what you're going to have is you're going to have the opposite. So now right here, because it's negative, so it's going to try to get sucked back into here, right? So this is what you would have as you would be going in that way. And so this is, I'm going to call this kind of number 1, and I'm going to call this number 2. And these two, of course, are vectors. So you would have an electric field number 1 and electric field number 2. Both are vectors, and you would have to find the superposition in between them. So you would have to do the addition of the two vectors to find out exactly what the electric field is. And if these two are identical, then actually, so what would happen in here, so these lines, it would be pretty neat, and you can convince yourself of this. I'm going to kind of remove this out of here so that I can present this to you, okay, and sketch it out. So what's going to happen is something like this, where, anywhere along this particular path, or this straight path, we know that everything is going to get sucked back into that negative Q, right? So your electric field is going to because it gets pushed away from the positive Q and it gets sucked in by the negative Q. But now anywhere that you put outside of here, then what's going to happen is going to start to create these types of field lines, right? Where it's going to be going something like this, right? So when it's going like that, and now the arrows are going to be something of that nature. So what that would be telling you is what would be if you put a positive test charge, how would it move, right? And it's actually showing you these lines and where the vector fields are. So they're going to be perpendicular to these particular lines. And of course, the same thing would happen on the bottom, okay? So this would be going like this, okay? And this would be going like this, okay? As you're going and having that through in here. So now along over here, you might kind of get pushed back into here, and it's interesting, okay? So and then in here it's going to kind of get pushed back out there, but as you keep going like this, this is going to create a pretty neat, nice form like that. And those are the new electric field lines now caused by two charges. And you can complicate this further, right? So you can now put 3 charges or 4 charges. But once you do that, we typically would probably use some kind of software tools like Desmos to try to map these things out for us so that it draws the actual forces and does all the calculations, because these would be caused by vectors. Now, I'll give you another one within here. So, if you had 2 charges and instead, let's say that they were both positive, okay? So that they were both positive like this. So what would actually happen in this particular case? So you know that a test charge is going to get pushed away from both of these, right? So, it's not because a positive test charge doesn't want to come to the positive and the other positive, so it's going to try to move away. And so very often, okay, so this is, a nice test for you to see if you understand how this works. So it's almost like in the middle in here, and the field lines would kind of look kind of strange like this, but they would go off in this direction, right? Where they're basically just getting pushed away, okay, in that way right there. So they're going to be pushed, okay, away in these directions, right, as you're going through. Okay, all the way, and they're going to be kind of going like that. Okay, so they're certainly, and then this one is going to look like this, okay, and this one's going to look like this. Because what is happening is that any point that you put on here, okay, so what happens is it gets pushed away from this charge, but it also gets pushed away from this charge, right there. So that's why it's going to kind of go off in there. It's not going to approach any of them. So you've created now new electric field lines, and you can now draw them out for yourself as you're going through. Now these ones are going to be a little bit more, okay, kind of straight as you're going in this direction, okay, but as they get pushed away in this side, they're going to get curved because the other one has an impact on it. So that's really neat to be able to see and try to see if you understand what is happening with these electric field lines. And please remember that the electric field is the actual charge that we have per coulomb. So coming back to, this equation right here and the units of this, okay, notice that this has the unit of newtons, and that is in metric standard unit, and this has the unit of coulombs. So what that tells us is that the electric field has the units of newton per coulomb. So per charge, what is the force that would be present on that? And if you want to know exactly what is the force, then all you have to do is multiply by the charge itself. Let's see an example of this so that you can see how to calculate, okay, on kind of the first initial go on these electric fields. So here are two charges. Now I'm going to make up all of these within here. So let's call, this particular charge and give it some number like 2.5, say times 10 to the negative 12 coulombs, make it negative. All right, so we're going to do that right there. And then let's say the other one, which is a little bit bigger, it looks like, so I'm going to put 4.5, times 10 to the negative 12 coulombs, and let's make this positive. All right. So now for yourself, if you had to describe what would happen at any point in time on a positive test charge, you should be able to do that, right? So it doesn't matter where you would put a charge. Okay, so let's imagine that this is, our charge right here. So if we put it here, if we put it here, if we put it here, if we put it right on the line, if we put it closer to here or further to here, okay, so it doesn't matter where we put it, we should know what is happening to this charge. So for instance, if we put it right there, we know, okay, a positive test charge would get sucked into this, but it would get pushed away from this one, right? So the positive one would push this away, this one would suck it back in. So notice you would have to do the superposition of those two vectors, okay? So the addition of those two vectors. So yes, break it down into x and y components for trigonometry, okay? And then calculate what the result would be, okay? So that's what would happen. If you have something right here, well, so this one is a little bit easier, okay? But you still have two vectors. So this one would get sucked back into this direction, and this one would get not sucked back into this direction, but it would get pushed away because of the fact that this one's positive. So you're going to get from the negative, and you're also going to get from the positive, this test charge would have been pushed away. So on this line, well, the vector field, okay, so the electric field would be pushed in this direction, right? And the same thing would happen. So you would have something like this happening, okay, on the electric field lines. And you can do this test for yourself. If your teachers ask you, try to just sketch the electric field lines where the force would be pushing it towards, you should be able to do that, especially if it's only two charges. If it's one, then it's automatic. You should know exactly what happens. Okay, so now let's try to see what happens. We want to find what the electric field is at this particular point. And let's imagine that this distance, because we're going to need distances in here, okay, and we're going to need a distance over here. So let's say, for the sake of simplicity, maybe this is 4 centimeters. And let's say, this is maybe approximately, 1.2 centimeters away. So let's try it. So the way that you do this and the way that you find the electric field at that particular point, again, you can only do it at a one point, right? Because the radiuses will change. So the way that we would do it is in this way. So number one, just simply take one of them. We're going to use superposition and assume that the other charge, the 4.5, is not there, okay? So we're going to find the electric force, sorry, the electric field from, and let's call this from charge number 1, and that is equal to just simply K times the charge, okay, so that's this charge right here that you have. So in this case would have been negative 2.5 times 10 to the negative 12, right? So this is what we have. The negative you can drop, you just have to know, right, that this particular vector, okay, is going to get sucked back into this direction. So we know that that negative just means it's going to be to the left. So you can technically drop this within here. And now you have your K, you have your charge, and you're going to be dividing it by the distance in between. Now the distance, be careful, you know, always change it back to metric standard units. Okay, so that's going to be 4 centimeters back into meters. And this would give you exactly what the charge, okay, would experience from that electric field. So that would have been the first one. So let me compute it, and let's see what we get. All right, so here's the first one. So what that means is that on that charge, this is going to be the first kind of, so this one is approximately 14 newtons, although I kept a few decimal places in there. So that's going to be to the left because it's coming from a negative charge. So that's the first electric field. So if there was nothing else, you're done. You found the electric field, and this is going to be newtons per coulomb. Okay, so newtons per coulomb. That's what we have. Now, we're going to have to do the same exact thing, but caused by this second charge. So now I'm going to kind of switch this back in here. So let's call this E2. And now, again, so the question is, which direction? Well, the direction, again, is going to be pushed away. So it's going to get pushed in this way because it's a positive charge. Right, so it's going to be pushed in this way. And let's try to find the magnitude. So the same thing. So K, this is going to be 4.5 times 10 to the negative 12 divided by, and now this is 1.2 centimeters, so 0.012 squared. And we can compute exactly what this is. Okay, so let me do that. All right, so here's the second one. So notice, you know, there's a big difference in magnitude. Well, A, the charge is bigger, but also it's much closer than it is to that negative charge on the other hand. Okay, so we have now these two, okay, within here. So it's much, much bigger. So obviously, you know, I'm not going to be able to draw this out because it's so enormous, okay, in comparison to that 14. So, you know, you can kind of extrapolate this further, but it's going to be in this direction. So this is going to be approximately 280, you know, 0.9, etc. newtons per coulomb. And now if you want to find what the total is, so the electric field in total is nothing else but the summation of the two. Now in this case, they're in the same direction, so it's easy to do the vector addition in here. So that's going to be just the addition of the two. So it's 280. Since I have it already on the calculator, I'll put the other one in. So 14.04, you know, 6, you know, 875. You can keep as many decimal places as, you know, your teachers ask you to. So let's say it's something like this, etc. It's newtons per coulomb, and it is to the left. It does have a direction. Now I think, you know, within here, I think I'd add everything to two significant figures. So let's keep it to 2. So 290 newtons per coulomb if you wanted to keep to 2 sig figs. So you have now found what the electric field would be at that point. And now the next thing might be, you might say, oh, okay, so now I know exactly at this point what the electric field is, what the actual direction is, and what the magnitude is. What if I wanted to find the force? Because this isn't the force. This is the force per coulomb. If you want to find the force, then what you have to ask is, what is the value of this charge? So now if someone comes along and says, oh, well, that charge, okay, now all of a sudden, so instead of being a test charge that I have, you know, so let's imagine that this particular charge is actually maybe negative, okay, so let's say that it's negative, and, you know, I'm going to, just for the sake of this particular example, so let's say that it's negative just for simplicity sake, you know, let's say maybe it's something like this, coulombs. So it's now negative. right? So the negative now will have an impact because of the fact that you know this is to the left, right? So you know this exact value in here of what that would be. So what you would have to do now is you would have to take whatever your electric field is and you would have to multiply this by the charge itself. Now, because it's negative, it's actually the force is not going to be to the left, but it's going to be to the right. And you have to be careful with that. So, you know, if I wanted to substitute this back in, I think it was 1 that I put in here. So 1 times 10 to the negative 10, I think it was. Okay, so to the negative 10, and I wanted to find out what that is. Now I have the exact force that is present, but it is to the right. Okay, so that's what you would actually find and you would experience on this. All right, so, you know, you've seen all of these lines. You've seen what the electric field equation is. Now, so notice, please keep in mind that we are utilizing Coulomb's law for this. So this is what you use, but this is related only to one of the charges. And if you have multiple charges, like we did in this example, then you have to calculate the electric field for each, with respect to each charge, and then you have to do vector addition of all of those charges. So in general, to summarize, the electric field is going to be equal to all of the electric fields with respect to all the charges that are present. So how many there are, this is what you're going to have to do. Deja vu. It's almost like, you know, talking about the net force and then adding up all of the forces. So this is going to be the sum of all of the electric, okay, fields that are present. And you may recall that the sum, the symbol is like this. And they are vectors, so if they're not if they're not unidirectional, then you got to use trigonometry, right, in order to do that. I did an example like that with respect to, for example, forces in Coulomb's law. I'll put up a link up above there, and you can do the same thing with electric field lines. All right, so lengthy video. I hope that you found this useful. Okay, you learned a little bit. We'll see you in future videos. Happy physics studying. Bye, everybody.